Now we recall the exponential and logarithmic functions and their properties. We will be using these properties to rewrite some exponential and logarithmic expressions in certain prescribed manners. Recall that if a is a positive real number that is not equal to 1, then the exponential function with base a is the function given by f of x equals a raised to x for all x in the set of real numbers. Here a is not equal to 1 because f of x equals 1 raised to x is just a constant function f of x equals 1. Now, whenever or as long as a is not equal to 1, this function is 1 to 1, and its inverse function is called the logarithmic function with base a. And the logarithmic function with base a is denoted in this manner. This expression is read as the logarithm of x to the base a. Some remarks: the domain of the logarithmic function with base a, which is the range of the exponential function with base a, is 0 to positive infinity, or the set of positive real numbers. Now, the exponential and logarithmic functions are continuous on their respective domains. The graphs will be shown later. Now, because these two are inverse functions of each other, then y equals log of x base a precisely when x equals a raised to y. Recall that an inverse function is obtained by interchanging x and y. So, the logarithm of x to the base a is the exponent to which the base a must be raised in order to get the value x. Now, if we take the composition, the logarithm of a to the x to the base a, then again, because these two are inverse functions of each other, then this gives us x for all x in the domain of the exponential, which is the set of real numbers. Similarly, a raised to the log of x base a is just equal to x for all positive values of x. Now, this is the graph of an exponential function with base greater than 1. It rises from left to right. On the other hand, when the base is between 0 and 1, the graph descends from left to right. In both cases, the graphs pass through 0, 1 because a raised to 0 equals 1. And note that the graphs are asymptotic to the x-axis. Now, these also illustrate the earlier remarks that an exponential function's range is the set of positive real numbers, and that an exponential function is continuous everywhere. So, the limit of an exponential function at any real number is just obtained by substitution. Now, let's observe the end behavior of the function. When the base a is greater than 1, the limit of a to the x as x approaches positive infinity is positive infinity. And the limit of a to the x as x approaches negative infinity is 0. So when the base is greater than 1, then as the exponent increases without bound, the exponential also increases without bound. Meanwhile, when the exponent decreases without bound, the exponential gets closer and closer to 0. When the base is When the base is between 0 and 1, the opposite relationship holds. The limit of a to the x as x approaches positive infinity is 0, while the limit of a to the x as x approaches negative infinity is positive infinity. Now, the logarithmic functions are the inverses of the exponential functions, so their graphs are obtained by reflecting the graphs of the exponential functions about the line with the equation y equals x. The uh, coordinates of the points are also interchanged. So because this passes through 0, 1, the logarithmic function will pass through 1, 0. And since when the base is greater than 1, this is asymptotic to the negative x-axis, then the logarithmic function with base greater than 1 must be asymptotic to the negative y-axis. And we obtain something like this. Okay, this is the graph of a logarithmic function with base greater than 1. And this is the graph of a logarithmic function with base between 0 and 1. Note that these functions are continuous on the set of positive real numbers. So the limit of a logarithmic function at any positive real number is obtained by substitution. Now again, let's observe the behavior at the ends of the domain. When a is greater than 1, the limit of log x base a as x approaches positive infinity is positive infinity, while the limit of log x to the base a as x approaches 0 from the right is negative infinity. On the other hand, when the base is between 0 and 1, the limit of the logarithm of x to the base a as x approaches positive infinity is negative infinity, while the limit of log x base a as x approaches 0 from the right is positive infinity. Please remember the graphs of these functions as we will use them later to evaluate some limits. Okay, you are also expected to know the graphs of these functions by heart in time for your next class. We also recall the following laws of exponents and logarithms. For instance, a to the r times a to the s is equal to a to the sum of r and s. A to the r all raised to s is equal to a to the product of r and s. And an exponent may be distributed over a product and a quotient. Note that exponents may not be distributed over sums and differences. Okay. The logarithm of 1 to the base a is 0 because a to the 0 is 1. Recall that the logarithm of a product is the sum of the logarithms. The logarithm of a quotient is the difference of the logarithms. And the logarithm of m to the c is equal to c times the logarithm of m. Now, this last statement is called the change of base formula. It tells us that the logarithm of m to the base a is equal to the quotient of the logarithms of m and a to a prescribed base b. We will use this later on. For now, let's try to rewrite, say, 2 to the 2x times 5 to the x as an exponential expression with a single base. Note that 2 and 5 are not perfect powers of each other. So we might have to use a property of exponents involving, sorry, properties of exponentials involving the same exponent. And we can rewrite 2 to the 2x as an exponential with exponent x because 2 raised to 2x is the same as 2 squared all raised to x. 2 squared equals 4, so we have 4 to the x times 5 raised to x. And now that we have a product and the same exponent, then we may combine these as 4 times 5 raised to x or 20 raised to x. Okay, we just recalled in the previous slide that an exponent may be distributed over a product. Next, let's try to find the exact value of the logarithm of 6 to the base 2 minus the logarithm of 15 to the base 2 plus the logarithm of 20 to the base 2. Note that 6, 15, and 20 are not perfect powers of 2. But since the base of each logarithm is 2, then we may combine these into a single logarithm. In particular, the difference of logarithms is the logarithm of the quotient. So we have the logarithm of 6 over 15 to the base 2 plus the logarithm of 20 to the base 2. And then the sum of logarithms is the logarithm of the product. So we have the logarithm of 6 over 15 times 20 Simplifying this, we obtain the logarithm of 8 to the base 2. And it so happens that 8 is a perfect power of 2, to which exponent must we raise 2 in order to get 8? It's 3. We will be using some of these processes later on in this course to rewrite some functions so that their limits, derivatives, or integrals may be computed more easily. Okay, so please review the laws of exponents and logarithms. Next, we will consider exponential and logarithmic functions with a particular base. First, consider the limit of 1 plus h to the 1 over h as h approaches 0. Note that the limit of the base is 1, while the exponent becomes infinite as h approaches 0. So you might be tempted to say that the limit is just 1 because the limit of the base is 1 anyway, and 1 raised to any number is equal to 1. But infinity is not a number, so that rule does not apply. The limit of this, if it exists, may not be equal to 1. Now, using more advanced methods, this limit can be shown to exist. But for now, we will just use a table of values to estimate the value of this limit. Okay, so just use a scientific calculator or some other computing device to verify the following table of values. For these values of h, we have these corresponding values of 1 plus h to the 1 over h. Okay, and we can also do this for values of h approaching 0 from the left. And note that 1 plus h to the 1 over h seems to approach a number that is around 2.71828. Now, the actual limit as h approaches 0 is what we call the number e. Okay? And we have the following definition. Euler's number e is defined as the limit of 1 plus h to the 1 over h as h approaches 0. Okay? This is the limit in the previous slide. This number is irrational, and to the first few decimal places, it is equal to this. And exponential function and logarithmic function with base e are called the natural exponential function and the natural logarithmic function, respectively. Now, for the natural logarithmic function, we have this special notation, ln of x. So ln of x is just the logarithm of x to the base e. Okay. Let's enumerate some properties. Let a, again, be a positive real number that is not equal to 1. Again, because these are inverse functions of each other, then when we take the composition, say ln of e raised to x, then we get x for all x in the set of real numbers. Similarly, e raised to the ln of x is equal to x for all positive values of x. Now, the ln of e is the logarithm of e to the base e, so that's equal to 1. Now, consider the logarithm of x to the base a. We will write this in terms of the natural logarithmic function. To do this, we will use the change of base formula. Recall, log of x to the base a is the quotient of log of x is the quotient of log x and log a to any prescribed base b. And in this case, we will take the base b to be e, so that we just have ln of x over ln of a. Similarly, we can write an exponential function with base a in terms of the natural exponential function. To do this, we will use this property. We will just plug in a to the x into x here and obtain that a to the x equals e raised to the ln of a raised to x. And now using properties of a certain property of logarithms, We may bring down the exponent, and we have e raised to x ln of 8. The last two remarks here tell us that any logarithmic function can be written in terms of the natural logarithmic function, and any exponential function can be written in terms of the natural exponential function. We will use these facts later on when we discuss derivatives of these functions. For now, please remember this last formula. A raised to x equals e raised to the exponent x multiplied by the ln of the base 8. Okay, so let's use that to say express 3 to the x plus 2 in terms of the natural exponential function. Okay, so we just recall the last remark. So applying this with a replaced by 3 and x replaced by x plus 2, we have the following. So applying the inverse property, a to the x equals e to the ln of a to the x, we have 3 to the x plus 2 equals e raised to the ln of 3 to the x plus 2. And then using uh, law of logarithms, we may bring down the exponent and have e to the x plus 2 times the ln of 3. Okay, so now we have rewritten this in terms of the base e. Again, this is just e raised to the exponent multiplied by the ln of the base. Now let's try to do this for x raised to sine x. Again, remember, we have e raised to the exponent multiplied by the ln of the base. So x raised to sine x is just equal to e raised to the exponent sine x multiplied by the ln of the base x. Okay, so we have e raised to sine x multiplied by the ln of this base x. Okay. We will use this process of writing exponentials in terms of the natural exponential function later on in this course to compute certain limits and derivatives. This concludes this portion on the logarithmic and exponential functions.